All right, so I've had a few requests to talk about 7.2, number 6. So this is a homework question. And the question wants us to find a basis for the domain of a linear transformation, for the matrix of the linear transformation that's relative to B, and we want to diagonalize that matrix. So this has a little bit of crossover from section 7.3. But the idea is first we're going to talk about the matrix relative, the matrix for this transformation. And so this is going to end up being the matrix. In our case, your numbers will probably be different, but this will be 4, 2, 2, 1. So that's our matrix. And then what we're trying to do is basically just diagonalize the matrix. And we'll talk about diagonalization as a systematic thing in 7.3. So you may have already seen that material, you may not. So that's our matrix M. In order to diagonalize, what we're going to do is we're going to start by finding the eigenvalues. So remember, that means that we're going to solve the characteristic equation. So that's where we take the characteristic polynomial and set it equal to 0. In our case, this means that we're taking the determinant of 4 minus lambda, 2, 2, 1 minus lambda, and we're setting that equal to 0. And so that means if we take this determinant, we'll get 4 minus lambda times 1 minus lambda minus 4 equals 0. And so just finding the determinant, and so that gives us lambda squared minus lambda minus 4 lambdas minus 5 lambda plus 4 minus 4. And so our eigenvalues will be 0 and 5. And so what we're going to do is we're going to take each of these eigenvalues. We're going to look at m minus lambda I for each of these eigenvalues, and then we'll find the corresponding null space. That's basically what we're doing. So that's called the eigenspace of this matrix corresponding to that eigenvalue. So if our lambda is 0, then we just have m minus 0, and that's just m. And so let me just write down lambda equals 0 here. And so m minus lambda I is just m. And so we'll find the null space for our matrix M. And so what this means is that we're going to take our matrix M, we're going to augment it with some zeros, and then we want to reduce this as much as possible. And it turns out, I'll let you kind of think about how this works, but it turns out when we do this, you can take basically negative 2 times the bottom row, add it to the top, and the top row will be gone. And then we can switch the first and second rows. There's a bunch of equivalent ways to do it, but that's what we get. So we get 2, 1, 0. And so let's let y be t, and then x will be negative 2t, because remember this first line basically says 2x plus y equals 0. So if we parameterize, we'll let y be t, x will be negative, and I made a slight mistake here. I'm glad I wrote this out, so just kidding. Let's let x be, so we have 2x plus y equals 0. So if y is t, then x is negative 1/2 t. So let's let x be t, and then y will be negative 2t. Okay, glad I caught that mistake. And so that's going to be the solution set. And so the null space of our matrix M is going to be all of the vectors x, y, where x is t and y is negative 2t, and here t is going to run through the reals. And so this is going to be basically all of the vectors that are t comma negative 2t, where t is a real number. Or you can think of that as the span of the vector 1, negative 2. Okay, and so that's the null space of M. And so our 1 and negative 2 will go here. For whatever reason, WebAssign wants to list these across each row instead of each column. That's fine. So WebAssign wants these as row vectors. And so anyway, so we did that for lambda equals 0, and then for lambda equals 5, we'll do the same thing. So we're going to look at m minus 5 lambda. That's going to be, let's see, so we're going to have 4 minus 5. So negative 1, 2, 2, and then 1 minus 5, so negative 4. So that's m minus 5 lambda. So the corresponding eigenspace, or the null space, corresponding to this eigenvector is, let's see, to find that, we're going to take this, augment this matrix with 0, 2, negative 4. This will work out to 1, negative 2, 0, 0. So again, just doing that quickly in my head, because the bottom row is a multiple of the top row, and I know that because 5 is an eigenvalue. Remember that being an eigenvalue is a value where this matrix has a 0 determinant. That means that when we simplify this, we'll have a row of zeros. And therefore, we can just basically ignore the bottom row. The top row, I'm just going to change the 1, the negative 1 to a 1. And so this becomes x minus 2y equals 0. So here we'll parameterize y equals t, x equals 2t. And so that means that our null space corresponding to this eigenvalue, or eigenvector, will be the span of, just cutting out a bunch of the stuff that we did before, the span of, so this would be 2t over t, so 2 over 1. So let me actually add a little bit more. This is the set of all vectors of the form 2t, where t is a real number, or you can think of it as the span of the vector 2, 1. And so 2, 1 is the second vector that would go here. So 2, 1. So we'd have 1, negative 2, 2, 1. Okay, so that's the process for number 6. And then just while I'm here, number 7 is very similar. So number 7 wants you to do the same thing, except the linear transformation that we have is between polynomials of degree at most 1. And so our linear transformation is we send the polynomial a plus bx to a plus quantity a plus 3bx. And so here our linear transformation, our matrix that we're going to have. So I like to think of this as kind of, if you kind of think about a plus bx as a matrix, this is basically sending a, b. So if I let a be the constant and b be the coefficient for the linear term, this is basically sending it to a plus 3b. And so our matrix that we're going to get is going to be 1, 0, 1, 3. And then you can basically repeat the process with this. Okay, and so you'll end up with various vectors. It's very similar. The only thing that you have to remember is that instead of listing your answer as matrices or vectors, you have to go back into the language of polynomials. So you have to kind of reinterpret. So anyways, just a little jump on number 7 there. Okay, so this is 7.2, number 7. Okay, but that's how we do those.